Make sure I'm recording this. We can see the screen, okay. Alrighty, so the example we were looking at last time, the instructions are basically use long division to perform the indicated division, and we were looking at question number 5. So this guy here, so you basically are given 9x to the third power plus 5 being divided by 2x minus 3. So I actually did want to show you what would happen if we did this as long division, and then I'll show you what was going on with the synthetic division. And I actually figured out I was the one making an error. Our math was good, but I left out one step that I was not doing to get the final answer. All right, so let's do this by long division first. So you've got 2x minus 3, which is our divisor, and we are dividing 9x cubed. Now we know we are missing the x squared term and we are missing the x term, so we're going to make some space for them, and you can put 0x squared and 0x if you like, or you can leave gaps. Alrighty, so as you can see, our leading coefficient in the divisor is a 2x. In the dividend, our leading coefficient is 9x cubed, or leading term is 9x cubed. So to match for that, you actually need to have 9/2 in your quotient. And then, of course, there's 1x in the divisor, x cubed in the dividend. So we, of course, need to have 2 extra x's in our quotient. So when you multiply 9/2 x squared with the 2x, of course, you can see your 2's will cancel out and we will end up getting 9x cubed, which is exactly what we want. And then, of course, we'll multiply 9/2 x squared with -3, which will end up giving us -27/2 x squared, which will, of course, go here. And then, of course, with division, we know we do subtraction. So that will end up giving us a -9x cubed and the positive 27/2 x squared. So in this case, of course, then our 9x cubes will cancel out, leaving us with only a positive 27/2 x squared. And then, we can bring down our 0x and the 5. Now to match for the 27/2 x squared as our leading term, what would we need to put up here in our quotient? So remember, since we have to multiply it with this 2x over here, we need to make sure we come up with 27/2, which means up here you will actually have 27/4 x, because we need one extra x there. So again, when we multiply 27/4x with positive 2x, you can see this 2 will cancel out the 4 on the bottom, making it 27/2. And then, of course, x times x will give us x squared. We will multiply 27/4x with -3, which again, we just end up multiplying it directly since nothing else cancels out, and that will give us -81x/4. And then, as always with division, we do subtraction. So that means this guy will become -27/2 x squared. This guy will become positive 81/4x. And then, of course, you can see the 27/2 x squared cancels out, leaving us with positive 81/4x. And then, of course, we bring down the 5. Now, to compensate for the 81/4 being multiplied with the 2x in our dividend, we, of course, will now add 81/8x to our quotient. So now you will have 81/8 x being multiplied into the 2x. So let's see, 81/8x multiplied with, sorry, I actually don't need an x, do I? Because I already have an x with my 2x. So we don't need the x, just 81/8. Yeah, just 81/8. being multiplied with positive 2x. So same thing, right? 2 will cancel out into the 8 and give us a 4 on the denominator. We will end up with 81 over 4x. And then same thing, 81 over 8 gets multiplied with negative 3. And remember, this guy comes out to be negative 243 over 8, which we will subtract from the positive 5. And then as we do subtraction here, again, the 81 over 4x will become negative, and the 243 over 8 will become positive, and we will end up with the 81 over 4x getting canceled out. And then when you add the 243 over 8 with 5, remember that had come out to be 283 over 8, which was our remainder for this division. So you have your quotient. You can see the quotient came out to be 9/2 x squared plus 27 over 4x plus 81 over 8. We got a remainder of 283 over 8. So now let's see, when we do synthetic division, what is the adjustment that we need to make? So I'll clear out all of, come on, buddy. Clear out all of this calculation here. And then let's take a look at synthetic division. So of course, remember, you have the 9 from the x cubed. We need to put a 0 for the x squared, 0 for the x, and then 5 for our constant term. And then when we are dividing, now again, remember, the divisor is 2x minus 3. So when we set that equal to 0 and solve for x, remember, we had come up with positive 3/2 after you get x by itself and move the 3 and the 2 to the other side. So technically, we are actually dividing by 1/2, right? 3/2 is 1.5. So dividing by 3/2, as you can see, we had gone through this math. So we had we had started out with bringing the 9 down. Then we multiplied 9 with 3/2, which is where 9 times 3 is 27. You get 27 over 2. When we add that with 0, of course, it just adds up as 27 over 2. Then we multiply 27 over 2 with 3/2. So we know 27 times 3 is 81. 2 times 2 is 4. So that fraction will end up becoming 81 over 4. Of course, adding that with 0 will just give us 81 over 4. And then when we multiplied 81 over 4 with the 3/2, again, we know 81 times 3 is going to be 243. And then, of course, 4 times 2 on the denominator will multiply to be 8. Now here, again, you are adding just positive 5 with positive 243 over 8. So we know that remainder will come out to be 283 over 8. So this is your remainder, which you will see does match the remainder from our long division. So 283 over 8 in both of them. But this is where I kind of got stumped, right? Because I was saying our quotient did not look the same as what, the answer key had. And you will see that's still the case because you've got 9/2 x squared. We only have a 9. You have 27 over 4x. We only have 27 over 2. And you've got 81 over 8, whereas we only came up with 81 over 4. And that's kind of where I was a little bit lost. But what I had forgotten was, most of the calculations we had done, you just had x by itself, right? We had x plus something or x minus something. We never had to deal with where you actually had a coefficient in front of your x, in the divisor. So to compensate for that 2 being on the x over here on our divisor, you actually take your quotient that we came up with and divide each of the numbers by 2 because you're compensating for this 2 over here. So either divide every number by 2 or basically multiply each term by 1/2, which is the same as dividing by 2. So your quotient will then end up becoming 9 divided by 2, of course, is 9/2 x squared. And remember, we're always 1 degree less than the polynomial. So you had a 9x cubed as your leading term. So this, of course, will become an x squared polynomial. So 9x squared, then you had a positive 27 over 2. So when you divide that by 2, your denominator becomes 4. So you will have a 27 over 4x plus 81 over 4 divided by 2, which again, your denominator will then change to 81 over 8. And now you will see, once you make for that adjustment, it matches the quotient from the long division. So now we've got 9/2 x squared, 9/2 x squared, positive 27 over 4x, positive 27 over 4x, and then plus 81 over 8, 81 over 8. So that was the only difference that we had to do. So our math was not wrong. I just had completely forgotten about that 2 being our leading coefficient on the x, and we need to make an adjustment for it. So now if you look at the answer key for this, you will see we were dividing by 2x minus 3. We got our quotient of 9/2 x squared, 27x, 81, 8. So all of that is multiplied between the divisor and the quotient, and then of course our remainder of 283 over 8. Now you will notice when we multiplied by 1/2, we only multiplied the quotient by 1/2. We did not multiply that with the remainder. So the remainder does not have to be compensated for that 2x, because obviously that was the other part I kept thinking, well, why is my remainder the same, but my quotient is not matching? And that's because of that one little step, but it's so crucial to remember that. So yeah, the 1/2 only gets multiplied with the quotient. You're not multiplying that with the remainder. And then you will see your long division and the synthetic division will come out to be the same. Questions on this one? No? Folks on Zoom, are we okay on that? Okay. All righty. Okay, so that was the example that I wanted to talk about. Sorry, something on Zoom. All righty. So this was, the example from our section 3.4. I did actually realize that even though we're not doing the Cauchy's bound here, I did want to talk about the rational roots theorem, because you do actually have questions on figuring out what your roots in your example might look like. Give me 1 second here. I think it's part of 2.3, if I remember. It's not in the applications. So you will see once you finish your synthetic division questions, yeah, it does ask you to figure out what your rational roots are. So we do actually want to talk about that. So that will come from section 3.5. So you will see I am skipping that first page of your text, but I will come to the theorem where we talk about rational roots over here. So let's take a quick look at this. Okay, so they are saying given a polynomial, you have f of x equals to a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1. And basically it's decreasing in order, right? So your largest degree and its coefficient is what we start with. So, imagine if it was an x cubed, then you go down to x squared to x till you end up with your constant term. So you're just decreasing in your degree as you go to the constant term. All of your coefficients are going to be integer coefficients. So all of these a values are all going to be integers. So they are saying if R is a rational zero of f. So we're basically saying if you have a zero, the horizontal intercept or the solution to your polynomial, we're just calling it R. And we're saying if that is a rational zero for your polynomial function, then R will have the form where you are taking the p-value, which will actually be the factor of your constant term. So that's a sub 0. So whatever that constant term on your polynomial is, you are going to take its factors. That's what we represent by p. And you are going to divide it by the factors of your leading coefficient, which is actually going to be the leading term. So they are saying basically take the factors from your constant term and divide it by the factors of your leading term, and then you look at both positive and negative combinations of those factors. So look at this example over here. Oh, and they're also saying that this list that we come up with the p divided by q plus or minus, they are saying it gives us a list of numbers to try in our synthetic division, because you can try those numbers out using synthetic division, and whichever one gives you a 0 remainder tells you that number is going to be one of your zeros for your polynomial function. So they're saying it's a nicer place to start than, simply guessing like, hey, what numbers might work. If none of the numbers in the list are zeros, then either the polynomial has no real zeros, or the real zeros are irrational numbers. So remember, they're specifically talking about rational zeros over here, and that's why it's called the rational roots theorem. So it will give you any number which can be written as a fraction with integer value. So you cannot have like a square root of 2 divided by 2 show up as a solution in this list that we are talking about, or like a number pi, or anything that's an irrational number will not show up in this list. So they're saying if we go through this list of rational roots, we do synthetic division to see if any of them give us a 0 remainder, and if they don't give us a 0 remainder, either our solutions are all imaginary numbers, which means they were not real numbers to begin with, or they could be real numbers, but they have rational numbers as their solution, so it's not showing up using this. So, there's limitation to this theorem, but it still helps you narrow down quite a bit. So remember, you are taking the factors of your constant term, so our constant term, and for now, you can ignore the negative sign, because remember in your list, you do put the plus or minus sign anyway, so you don't have to worry about the signs right now. So you take your constant term, and we know its factors are going to be 1 times 3. You take your leading coefficient, and we know its factors are going to be 1 times 2. So because these are prime numbers, this list is actually going to go down pretty quickly. If they were non-prime numbers where they had multiple different combinations as its factors, you would have a much longer list. So remember, this represents the p value, this represents the q value, and you are always setting it up with p numbers on the top, q numbers on the bottom. So you will be making your list as, I don't know, I guess I'll start out with 1 for the p value. So 1 divided by 1 from here, 1 divided by 2 from here. Then we can move on to 3. It will be 3 divided by 1 from here, and then 3 divided by 2 from here. And then you put your plus or minus signs on them. So that's a total of 8 possible roots that we are coming up with. And then, of course, you can clean it up. So 1 divided by 1 is just 1. 1/2 will stay the same. 3 divided by 1 will just become the number 3. And then 3/2 will stay the same. So you can see that's how we come up with the list. Now, we are not saying that all 8 of these are your solutions. They're not, because it is just a 4th degree polynomial. You're only going to have a maximum of 4 roots. But what this does is it gives you a starting point, and it's saying, okay, start by checking, maybe start by dividing by +1, by -1, see if you get a 0 remainder. If that doesn't work, move on to +1/2 or -1/2, and keep going till you get through the end of these 8 numbers, and then you can come up with your answers. Now, sometimes My open math will let you do plus or minus. Does it give you plus or minus in your list? It does not. So you may actually have to then write it out separately. So you may have to list it as +1, -1, +1/2, -1/2, +3, -3, +3/2, -3/2. I don't think it will matter if you have it in the order of smallest to largest, largest to smallest, because they're just saying enter a list of mathematical expressions according to, yeah, so no instructions like they have to go from smallest to largest or, negative, positive first. So you should have the flexibility of writing out your answers just as a list of numbers separated by commas. And then basically they kind of build up on that and they say, okay, if you look at this example over here, we are given, I think this is the same expression. Yeah, so same polynomial, f of x is equal to 2x to the fourth plus 4x cubed minus x squared minus 6x minus 3. And they're asking us to find the horizontal intercepts, which again are the zeros for this. Now they went with calculator technology, but I'm not going to worry about that since we're not really talking about the Cauchy bounds over here. The Cauchy bound, I guess I can give you a quick overview, just basically tells you what is the smallest possible answer you can get and what is the largest possible answer that you can have for your polynomial. So it just kind of helps you set up like the lower bound and upper bound to see which, I like in this example, you can see they're using the calculator, but they're basically saying the numbers will fall between -4 and +4. So any answers you have outside of that can be ignored. Basically, that's what the Cauchy bound does. And then, of course, we have our list of possible rational zeros that we just did in the previous example. So now you can see they started out by using -1 because they could see on the graph that it looks like at -1, our graph is crossing the x-axis at. So they tested with -1 using synthetic division, and you can see that ended up giving us a 0 remainder. So that tells us that -1 is definitely one of our roots for this example. And then they said, okay, that's good. Remembering that f is a 4th-degree polynomial, we know that our quotient is a 3rd-degree polynomial. So obviously this guy here would come out to be a 3rd-degree polynomial. They're saying if we can do one more successful division, we have knocked out the quotient from now being a 3rd-degree polynomial to a 2nd-degree polynomial. And they're saying, if everything else fails, we can always use the quadratic formula if you have, just a 2nd-degree polynomial to find your zeros. So they are saying since there are no other rational zeros to try, we will basically continue with -1 again. So they take the -1 and they divide it back into your quotient because they're going with the idea of multiplicity, right? Like they're trying to see maybe -1 is, to the 2nd power. So they try using that same -1, and now you will see they're using +2, +2, -3, -3 as the polynomial. They go through the synthetic division, and that does in fact end up giving them a 0 remainder, which does actually tell us that we have a multiplicity of -1 has a multiplicity of 2, but actually they are saying also the shape of the crossing at x minus 1 leads us to wonder if 0 that exists at x minus 1 may have a multiplicity of 3. And what are they talking about? Look at the shape of the graph over here. That looks like a 3rd-degree polynomial because remember your x cubed function has that s kind of shape as the base function. So they are saying it's possible that x minus 1 may have a multiplicity of 3. And they are saying, okay, success again. So now your quotient has been broken down to a 2nd-degree polynomial, since this you can set equal to 0 and solve for it, you can see that ends up giving us a positive negative square root of 3/2. When you simplify it, it comes out to be positive negative square root of 6/2. So they are saying since the 4th-degree polynomial can have most 4 zeros, they are saying even though the shape of the graph looked like it's a cubed function, or at least that shape of a cubed function, they are saying once you look at the final answer, it actually looks like the -1 only had a multiplicity of 2, because then of course we are getting 2 roots from here, right? You're getting plus and minus square root of 6/2. So that's kind of where the idea of the rational roots comes in, because it says, we can give you kind of this list of options, and then you can kind of choose those numbers and see if any of those will end up giving you a rational zero, and you can use that to, kind of get a starting point of where we can start by finding our rational zero. So those are kind of the examples that they have here in the rest of the section. But mainly, I really just want you to focus on the definition here and then this example for rational roots, because I think that kind of lays out what they are asking us to do here in this set of examples. Okay, so let's actually take a look at this one, because this one gives us multiple different options. So let's break this guy down. All right, so they're saying according to rational roots theorem, what rational numbers are possible roots of this polynomial? So again, remember your p-value will come from the factors of 15. And again, I'm ignoring the negative sign for right now. And then the q value will come from factors of 5. So remember, p represents the constant term, q represents the leading coefficient. So now 15, remember 15 can be broken down into 1 times 15, 3 times 5. Is there any other combination which will give us 15? No, right? Because once you get to 3 and 5, you're not able to break it down any further. Now, if you look at 5, 5 being a prime number will only break down into 1 times 5. So remember, to find those rational roots, it's plus or minus p over q. So when you start listing these guys out, the p value needs to go on the top. So I'll go in order. I'll start with 1. So it's got to be 1. And then, of course, you'll be dividing by the q values, right? So once with the 1, once with the 5. So plus or minus 1 divided by 1, plus or minus 1 divided by 5. So we're done with that. Then I'll move on to number 3. So plus or minus 3 divided by 1, plus or minus 3 divided by 5. So we're done with that. Then we move on to the number 5. So it's going to be 5 divided by 1, and then plus or minus 5 divided by 5. And that leads us to the last one, which is 15. So plus or minus 15 divided by 1, plus or minus 15 divided by 5. And then we can clean this up. So we will have plus or minus 1 divided by 1 is 1. Plus or minus 1/5 will stay the same. Plus or minus 3 divided by 1 is 3. Plus or minus 3/5 will stay the same. Plus or minus 5 divided by 1 is 5. Plus or minus 5 divided by 5 is 1. So that's actually repeating, you will see from here. So we don't have to list it out twice. All right, so that was 5 divided by 5. And then plus or minus 15 divided by 1 will be 15. Plus or minus 15 divided by 5 will be 3, which is again repeating, right, from here. So everything that's repeating, we do not need to write it out twice. So then if we put our list here, and I know again, I apologize, it's writing on top of writing, but since it's not going to let us do the plus or minus symbol, we'll start with +1, -1, and I'm not putting any spaces between these numbers, just comma. So +1, +1, -1, +1/5, -1/5, and it looks like it's asking me for parentheses, so I'll get to that in a minute. 1/5, what else? +3 -3, +3/5 -3/5. Plus and minus 5, plus and minus 15. Is that it? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Do you want me to put parentheses or you don't want me to put parentheses? You don't want me to put parentheses. Okay. So again, I know, like I said, it's writing on top of writing, so I apologize, but I'll clean that out for just a minute. So you can see we didn't have to put the repetitions in. You're just separating each answer by a comma. You don't have to put a space, and we didn't have to use those, I don't know, I call them curly brackets, but you didn't have to use those either. You're just putting your list of numbers. But yeah, that basically is what you do for rational roots theorem. Questions on that, guys? Everybody on Zoom feeling okay about that? Yeah? Promise I'm not seeing you. All I see is a bed. Where are you? Ah, there you are. All right, thank you. So work on those, and obviously, as always, if you guys have any questions, you want me to go over anything, feel free to ask for help. But that was from section, what is it, 3.5, but literally just this part, right? We're not diving deeper than any of that. Okay, section 3.6. Now, you don't really have questions as far as this chapter goes that we're working on, where it talks about complex numbers, but I do actually want to talk about complex numbers because we will run into examples where you will be using imaginary numbers and complex numbers. So I want you to know what they look like. Now, you've probably seen this in your previous courses, but I want to make sure everybody's comfortable with complex numbers and, able to work with those. Because also your quadratic equations, you're not always going to end up with real number solutions. Sometimes you will end up with imaginary solutions. So yeah, let's take a look at this. So, and we had actually come across this when I had talked about one of the examples where we got no real solutions and you just ended up with an imaginary solution. So we're finding the zeros of polynomials, and they're saying at some point we may be faced with a situation where you have x squared equals -1. Now, if you try to find the solution to this guy, x squared equals -1. Now, of course, we know we would start by taking a square root on both sides, which would give us a plus or minus x equals plus or minus square root of -1. Now, I know I had shown it to you at that time, but let me just come up with our scientific calculator. So imagine what happens if you try to plug in square root of -1, you will see your calculator is going to give you undefined. Sometimes the handheld calculators tell you error, right? So they'll tell you, well, there's no solution, and that's because this is where we are getting into the territory of imaginary numbers. We're not dealing with real numbers anymore. So we actually define this number where you have square root of -1 as the imaginary number I. So we call it the imaginary number I. So technically the solution to this equation that we were trying to solve, x squared equals -1, your solution to that actually comes out to be plus or minus I, because we're saying your solution is not a real number anymore. It's an imaginary number. So I guess another thing that I want to mention is, if you look at our number system, your complex numbers are a family, right? They're the big group of numbers that get split into real numbers separately and imaginary numbers separately. There is no overlap between these two sets of numbers. And then once we get into reals, that's where we're talking about integers, whole numbers, rational, irrational numbers, and all of those fall under the real. But your imaginary is where anything that has the not the real number, the imaginary number I falls under that category of imaginary numbers. Another thing that to keep in mind when you're kind of looking at these complex numbers here is that complex numbers are written in the form of a plus bi. So the a is what represents the real number set, and the bi is what represents the imaginary number set. So if, basically the idea is if your b value was 0, so, imagine in real numbers, we are saying the b value is equal to 0. So, 0 times I, that ends up becoming 0, and you're just left with a. But when we are talking imaginary numbers here, of course, your b value is not equal to 0 because it keeps the I, right? It keeps that imaginary number. So I think that's the simplest way to think about what complex numbers are. They split up into imaginary and real numbers, and they are two subsets of the complex number set. So the biggest thing to remember when we are working with imaginary numbers is that we define I as square root of -1. It's not just -1, right? It's with the square root symbol. So that's your imaginary number I, and they're saying any real multiple of I is also going to be an imaginary number. So if you have the number 2i, that's imaginary. If you have the number -5i, that's imaginary. So they're saying basically if you have, any number which is being multiplied by I, that whole number becomes an imaginary number. So look at this guy here. You have square root of -9. So what I can do with this guy is I can separate the negative from the 9, and I can write it as -1 times 9. And then, of course, using the square root properties, I can separate them into two separate square roots, and I can come up with square root of -1 times square root of 9. Now we know square root of -1 is the imaginary number I. So you can break that guy down. Now, what happens by separating that negative sign? We can now simplify the square root of 9 because we know square root of 9 is 3. And this guy will actually become 3i. And do keep that notation in mind. You don't want to write I in the front and 3 in the back. We do always put the number first and then I after it. So you will never see like I3. Because that can get confusing. So you will always see 3i. So just a notation thing to kind of keep in mind, I guess. Oh, I want to get rid of you. How do I get rid of you? There we go. Okay. Hello. All right, there we go. So you can see your textbook kind of shows you the same sort of math, and we come up with 3i. So here is the description that I was telling you guys. So complex numbers are usually denoted by the letter Z. So you can see we're saying Z equals A plus BI. Now, A by itself and B by itself are representing real numbers. But as soon as we put that I on the B, remember this property kicks in. So since you are multiplying the B with the I, that's what makes it the imaginary part of the complex number. And because A does not have the I on it, that's what makes it the real part of the complex number. And then obviously I is still the same definition, square root of -1. So just your general format for the, and again, yeah, we do put the A first and then the BI. So you will never see, BI being placed first plus A at the end. So we again kind of follow this same notation where A is in the front and then BI is in the back. So we do want to do some basic calculations over here. So we are talking about, addition, subtraction, multiplication, division, those kind of things. So we are saying, okay, before deep diving into more complicated uses of complex numbers, let's do addition and subtraction. We are basically saying you add them like terms. So add like terms, which means the real part gets added with or combined with the real part, the imaginary gets combined with the imaginary. So along the same lines of, imagine if you had 3x plus 5 and you were trying to add it to, I don't know, 7x minus 2, right? We would combine the x terms together. We would combine the constant terms together. That's exactly what you do with real and imaginary part. So real gets added with the real part, imaginary with the imaginary. So you've got 3 minus 4i being added to 2 plus 5i. Now, of course, since this is a plus sign in between the two terms or the two numbers, we don't really need the parentheses. So 3 plus 2 will give us 5. Negative 4i plus 5i will give us plus 1i. And again, you don't have to write the 1, you can just say 5 plus I. So just like I said, think of, that I as what if it was an X term? How would we combine them together? That's the exact same thing you do here. Subtraction, you do have to be careful. So they are saying we are subtracting 2 plus 5i from 3 minus 4i. So you can see that set up over here. You're doing 3. Actually, I may need more space. You're doing 3 minus 4i. And from that, we are subtracting 2 plus 5i. So remember with subtraction, that sign does distribute between the second number. So you will end up with 3 minus 4i from our first number. And then after distributing that negative sign, you end up with -2 minus 5i. So of course, the signs will change. And now you can combine your like terms. So 3 minus 2 will give us 1. Minus 4i minus 5i will give us -9i. And of course, you can see that answer here. So just like we did with real numbers, it's honestly the same process when you are adding and subtracting. Just need to remember that, hey, that minus sign will distribute into my second number, and I have to be careful about that. Okay, so take a minute, look at these two examples, and let me know if you have any questions, adding and subtracting complex numbers. Questions, ladies? No? Okay. All right, let's see what happens when we're trying to multiply and divide. And honestly, for even multiplication and division for that matter, a lot of it should look similar to what we've done in the past. So here you can see we are trying to multiply 4 with 2 plus 5i. So same thing, right? That 4 will get distributed inside the parentheses, actually. Let me make this kind of bigger. Yeah. So distribute that 4 inside the parentheses. So 4 times 2 will give us 8. 4 times 5 is 20. And then, of course, don't forget the I. So 4 times 2 is 8. 4 times 5i is going to be 20i. Now, if you were taking two complex numbers like, what did we have in that previous set? Let's imagine if you were taking these two numbers here and multiplying them, so if you had, stop doing that. 2 plus 5i being multiplied with 3 minus 4i, literally, same thing as we did with real numbers, you would use FOIL to multiply these. So let's pick an example maybe for multiplication. Let's see what they have. Yeah, so let's maybe look at 15. So you can see we are given 2 plus 3i being multiplied with 4 minus I. So we will use FOIL to do this. So remember, you take your first terms and multiply together. 4 times 2 is 8. Then we take our outer term, so that's 2 times negative I, which will become minus 2i. Then we do the inner term, so that's positive 3i times 4, so that will be positive 3 times 4, of course, is 12, and then you put the I on it. And now we are doing the last term, so that's positive 3i multiplied with negative I. So positive times negative is negative. 3i times I will, of course, become I squared. And I will talk about that here in a minute. So again, remember, I is square root of negative 1. So same thing, combine like terms, and you will see your middle two terms are like terms, so we can combine them together. Negative 2i plus 12i will give us positive 10i. And then we have the minus 3i squared. Now, the I squared will actually simplify. And what you need to remember is that when we define I as square root of negative 1, well, if you're going to do I squared, that means you're putting a square on the square root of negative 1. So here what happens is your square and square root cancel out, giving you I square as negative 1. So you can actually replace that I square in your problem or in your product after you're done multiplying. So we have negative 3 times I square. I'm replacing the I square with negative 1. So you will see these guys will multiply to become positive 3. So we end up with 8 plus 10i plus 3. And now you can combine the 8 with the 3, which will, of course, end up giving us 11 plus 10i. So you will actually be able to consolidate this down to just a single complex number after you are done multiplying both of them. And honestly, same thing will happen in number 17. Now for number 17, you can use FOIL again, or you can use the rules of multiplication. So if we wanted to do, let's say 17. So you have 4 minus 2i being multiplied with 4 plus 2i. Remember the rule from our multiplication. If you're multiplying a plus b with a minus b, it comes out to be a square minus b square because your two middle terms cancel each other out. So if you recognize that, hey, both of them have a 4, both of them have a 2i, it's just plus or minus that's different between the two factors, I can use this property. So this will give me a square, so that becomes 4 square for the first term, minus b square, which is, of course, the 2i, and you're doing 2i quantity squared. So, of course, then you will see we get 4 4s are 16, minus 2 squared is 4, and then, of course, the I will also square and become I square. And then same thing, right? I square represents negative 1. So that will become 4 times, or actually negative 4 times negative 1, which will then, of course, end up becoming 16 plus 4. And this guy actually just comes down to be a single number. It adds up to 20. Now, like I said, you can also use FOIL for number 17 if you don't remember this rule over here, but you should still get the same answer. So let's look at our solutions for 15 and 17. So you can see right there, 15 came out to be 11 plus 10i, which is what we had here. And then 17 came out to be 20, which is what we just came up with. So yeah, those numbers will in fact clean up, I guess, when you are doing these multiplications. Yeah, it's just kind of sad that they didn't show you that in the example from the textbook. They just did, a real number. Why are you not moving? Yeah, they just did like a single number 4 instead of doing two complex numbers together.
I think it was for 15. We got 11 instead of 12.
Yeah. So we had,
The answer was 12.
was it 12? I thought I saw 11.
I think I saw 12.
Let me go back to the answer key. Yeah.
Oh, yeah, there, yeah.
I don't know if you were maybe
Oh,
looking
yeah.
at that guy, but yeah, 15 we had 11 plus 10i, and then 17 we had
Okay.
20. Yeah. Alrighty. Sounds like, man, that'd be bad if I cannot add numbers now. All right, guys, so that was multiplication. Now let's look at division over here. So you can see in this example, we are dividing 2 plus 5i by 4 minus i. Now they are saying, when dividing two complex numbers, we have to devise a way to write this with the real part and the imaginary part. So kind of like separating the real from the imaginary part. So they're saying this is where we start this process by eliminating the complex numbers in the denominator. So, getting rid of the complex numbers in the denominator. And to get rid of that, we actually have to use what we call as the complex conjugate. So complex conjugate is basically where, honestly, what we did in number 17. So the complex conjugate is where you multiply the denominator by its conjugate, where the terms stay the same, but the sign changes. So they're talking about how the sign on the imaginary part is changed. And I would say don't even worry about imaginary part or not. Basically, the idea is if the denominator has a minus, its complex conjugate will have a plus. And the reason we are doing that, like I said, just as we did in number 17, actually, I may be able to just bring up our example. So you can see these number 17s were complex conjugates of each other because you had a 4 minus 2i being multiplied with the 4 plus 2i. So your terms were the same. It's just the sign in the middle that changes. So when we multiply them, you can see it ends up becoming a real number, right? So that's what happens when you do that in division. If you multiply your fraction by the complex conjugate, you actually help get rid of the complex number in your denominator, and then the math will become easier for us to solve. So you can see in this example, since you had 4 minus I in the denominator, we multiply both the numerator and denominator by its complex conjugate, 4 plus I. So of course, on the denominator, you will have where you take the 4, square it, take the I, and square it. So of course, you can see that will end up becoming 16 minus -1. And yeah, it does help to remember that I square will always be -1. And this guy will end up becoming 16 plus 1, which will be 17. So now you will just have 17 on the bottom, and then, of course, use FOIL on the top. So that's kind of where I would imagine these guys are also heading. So yeah, so they're taking the numerator, 2 plus 5i, multiplying it with 4 plus I. You can see that. They did the FOIL, add the two middle terms together, which gives you the 22i, replace the I square with -1, which will make this -5. 8 minus 5 is 3, so you can see your numerator cleans up nice and well. On the denominator, like we just saw, when you multiply the denominators, it will end up basically cleaning up into number 17. And then you end up with, Can I get this on the same screen? Yeah, you can take your 3 plus 22i from the numerator, divide by 17 on the denominator. And then this actually is how we write out when you have, fractions. In your complex numbers, we do not leave them as a single denominator. You do separate the real part and separate the imaginary part because we want to know 3 over 17 represents a real number. 22 over 17i represents the imaginary number. So yeah, please make sure you separate that denominator. Okay, so it looks like they did actually come back and talk about multiplication here with two imaginary numbers completely. So 3 minus 4i being multiplied with 2 plus 3i, and you can see that guy is coming out to be 18 plus i. And yeah, here's your definition for complex conjugate. So basically, you just change the sign in between the two numbers, but the a and the bi parts will stay the same. And then you can kind of see the notation they use when they're talking about complex conjugate. So by putting the bar on top of it, we're saying we're looking at its complex conjugate. For a plus bi, it will be a minus bi. And again, we use complex conjugates mainly in division if you have the imaginary number on the bottom, right? Because we want to get rid of that imaginary number and not have it anymore in the denominator. So this is kind of what I was talking about. Sometimes when we are solving quadratic equations, we don't always come up with real number solutions. Sometimes we do have imaginary solutions. So if you look at this example over here, we are given x squared minus 2x plus 5 as our quadratic function here, and they're asking us to find its zeros or even horizontal intercepts. So remember, this is where you use your quadratic formula, which is x equals negative b plus or minus b squared minus 4ac and everything divided by 2a. Of course, your a, stop it. Your a comes from the leading coefficient, the middle term gives you the b, the constant term gives you the c. So you can see we have -2 for our b value. So by the time you do the negative from the formula and -2, the two negatives become positive. So that's why this guy is positive here. Plus or minus inside the square root, you will see we are supposed to have b squared. So that's the -2 squared minus 4a. A is the leading coefficient of 1. So that's where the 1 comes from. And c, of course, is our constant term. And then divided by 2a on the denominator. So clean that up and you will see basically if you end up with a negative sign inside your square root, you are going to have imaginary. If that number on the inside had been positive, you get a real answer. If the square root comes out to be 0, you actually only get one answer. And there is actually would I call it a test? I guess you can call it a test. It's called is it just discriminant or is it discriminant theorem? No, I think it may just be called discriminants. Basically what it does, it has you check what the value of the inside of the square root will come out to be, which you can see will be that b squared minus 4ac. So the idea is if the inside of the square root comes out to be a positive answer, you will have two real solutions to your quadratic function. If it comes out to be 0 on the inside of that square root, you will have just one real solution. And if you get a negative inside of your square root, like this example has, this is where we get two imaginary solutions. So you can literally just take that b squared minus 4ac value and kind of look at, I guess, this table, and you will know what you get. Yeah, so since we have the negative square root of 16 here, again, remember how I showed you before? You can separate that negative sign from the 16, and make it square root of -1, square root of 16. We know square root of -1 will become I. Square root of 16, of course, will break down into 4. And you can see that's where that 4i is coming from. And then, of course, you get, positive 2 from the first term here, and then your denominator was also a 2. And then, yeah, just clean that up to come up with your simplified answer. So basically, at this point, what we have is, and I'm going to, clean up from here. So you basically have 2 divided by 2, right? Separating that. Then plus or minus, I have 4i divided by 2. So of course, 2 divided by 2 will become 1. 4 divided by 2 will become 2i. So you end up with 1 plus or minus 2i. And again, if you need to type solutions in your answers and they don't give you the plus or minus sign, then you just separate them as 1 plus 2i, comma, 1 minus 2i. But you have your 2 solutions. Obviously, you will see same thing is happening over here. With this guy, you have 2x squared plus 3x plus 4. So once you get your A, B, and C answers into your quadratic formula, you can again see we ended up with square root of -23. Now, 23 by itself is a prime number, so you will see 23 does not break down anymore. But look at the notation of how we write this with a square root. Now, if you had an integer, we put the 4 in the front and then the I in the back, right? But when you have a square root symbol, you actually put I in the front, square root in the back. So the notation actually goes AI square root of B. So if you have just an integer number, you put the number in the front, the I in the back. If you just had, no number in the front, but you had just I with the square root, you put I in the front, square root in the back, like they did here. And then if you have something like, I guess I'm just going to use a combination of this. If you had both the real part and the square root, the I would be sandwiched in the middle. So you would put the integer in the front, I in the middle, and then the square root in the back. So this is actually the breakdown if you get one or the other or both of those numbers. But yeah, ultimately you still have that I in there because we had a negative inside our radical and we ended up, getting an imaginary solution here. And then same thing, separate your denominators to separate your imaginary from the real part. Okay, so one thing they are actually talking about is if you're solving, I think usually you get both the complex conjugate parts together, but sometimes, and I don't know if you guys will see this, it used to be a question in our old textbook, but I don't think it's in this one. But they would sometimes give us like, if the solution of a quadratic function is, 1 minus 2i, they would ask you to find its other quadratic solution. So what you need to know is basically the complex conjugates come as a pair when they are solutions to a quadratic function, which means you're not just going to get 1 minus 2i in the solution, you are also going to get 1 plus 2i as a solution also. So they do come together as a pair. If they only give you one, you can automatically assume the other one is also going to be a solution to your quadratic. Actually, it should also work for polynomials. So let's take a look at this little explanation here. So two things are important to note. First, the zeros of 1 plus 2i and 1 minus 2i, which is, this one here, are complex conjugates. This will always be the case when we find non-real zeros for a quadratic function with real coefficients. So that's what they're talking about. They will always come together as a solution. Second, we could write our original polynomial, which is x squared minus 2x plus 5, by using these complex conjugates as, our roots. So you can have, the factoring would be where you do x minus, and then you put one of the complex conjugates here. And then for the other factor, it would be x minus 1 minus 2i. So you're basically having the format of, x minus something and x minus something. And we know that because the middle term is minus, but the constant term is plus. So we know both of these factors will have a minus sign. But then here, you're just putting one and the other of your complex conjugates to kind of break it up into a factored format for your polynomial. So if you really wanted to, the factor and remainder theorems would hold if you wanted to check for that. And then here they actually get into deeper with how, you can come up with non-real or imaginary solutions for your polynomials, which are greater than a second degree polynomial. But I, again, don't think you will be running into that because, we've tried to not deep dive too much into the complex numbers, but I do want you to have that basic information, that basic understanding of what complex numbers look like, so that if you do come across them, you're not stumped by, oh my God, we never talked about complex numbers. I don't know what I'm doing. Questions on those, guys? Everybody on Zoom doing okay? Again, you guys have been very quiet. Alrighty. So yeah, even though that was, like I said, officially not a section separate by itself, I do want you to know that. So we are officially done with 2.3 and 2.4. Again, remember I told you guys to work on that. So we'll dive into section 2.5 where we need to talk about rational functions. I just wanted to let you know your section 2.2 homework is due tonight at midnight. So please don't forget about that. And section 2.3 homework is due Friday. I did move the section 2.4 homework to Monday of next week. Since, we just got done talking about rational roots theorem today, I wanted to give you a little bit extra time to work on the 2.3. So yeah, your 2.4 homework got moved to next Monday. So just kind of keep that in mind. Okay, so when we are talking about rational functions, remember we're basically talking about any function that can be written with, well, in a fraction format, but it can go a little bit more than that. So let's take a look here. So we're basically saying we have, in the previous section, built polynomials based on positive whole number power functions. In this section, we're exploring functions based on power functions, which can actually also have negative integer powers, and it's called rational functions. So yeah, we can talk about rational functions, with polynomials, but basically to remember when we are discussing rational functions is that they will be in the form of a fraction. So you could have like a polynomial on the numerator and a polynomial on the denominator. Now, you're not always going to have something, big and complex, but anything that can be broken down into a numerator and a denominator, with the polynomial on the top, polynomial on the bottom, would be called a rational function. And then, of course, we're talking about where you could also end up with negative integer powers on these functions. So this example here is talking about you plan to drive 100 miles. Find a formula for the time the trip will take as, based on the function of the speed you drive. So basically, we want to know how long will it take us to drive 100 miles based on the speed we are driving at. So, obviously think about it in terms of the faster the speed is, technically the lesser the time should be, right? The slower the speed is, the more time it should take us to reach our destination. Now, in practicality, that may not always be true because there are so many other factors, right? You have to think about maybe construction, maybe how many cars are going to be there. Is it rush hour, time of the day? In my case, how many cops are out there because I don't want to get ticketed. So it can be a lot of different factors. But if we just take the general setup of the problem, then more speed, less time, less speed, more time. So you can see this will be a inverse function as we set it up, or a inverse relationship rather. So in this case, we are saying that we know speed, which is the variable v, and it's for velocity, but we're calling it for speed or rate. And then t, of course, represents the time in hours. So we know speed multiplied with time gives us distance. And so since we know our distance is going to be 100 miles, that's a constant factor, we're basically saying, well, speed multiplied by time should equal 100. So if we want to know how long will it take us to get there based on our speed, you divide both sides of this equation by v, right? So divide both of these by v, and you get t equals 100 over v. Now, since they're asking it for us to write it as a function based on speed, this is how you formally end up writing it. So time is based on speed. That's 100 divided by v. But what they are doing is, they're saying, okay, we know the denominator is raised to the first power. So if I wanted to write it with a negative exponent, just bring the v to the numerator, and that exponent would end up becoming -1. So you can either leave it as a rational function where you leave it as a fraction, or if you want to convert it into, a negative exponent rational function, then it would end up looking like this. Obviously, they both represent the exact same function value. So they're saying this kind of relationship can be written using a negative exponent. It is more common to leave it as a fraction. And I would definitely recommend doing that, to leave it as a fraction instead of working with negative exponents. This particular example, as I also mentioned, is going to be an inversely proportional relationship where one quantity is a constant divided by the other quantities. Think of a general example like this. One of our basic toolkit functions for rationals is 1 over x. And you can kind of see, and we had talked about these examples previously when we talked about our toolkit functions. You can see what the graph of 1 over x looks like. We are saying there's several natural phenomena, such as gravitational force, volume of sound, behave in a manner inversely proportional to the square of another quantity. So in this case, we're talking about if you had a constant value k, your volume is actually going to be inversely proportional to the distance from the source of, wherever the volume is coming from. So it's volume V is equal to K divided by D squared, which again is a transformation on this function. And you can see what the graph for 1 over x squared ends up looking like. So both of these are examples of rational functions. This one was just 1 over x. This one was 1 over x squared. So look at how the shape of your graph changes from 1 over x to 1 over x squared. So let's start by looking at the reciprocal function 1 over x. As you well know, dividing by 0 will not be allowed, because if x was equal to 0, we would of course end up with an undefined problem. And so in this case, x would not be part of our domain, and the function would be undefined, as I mentioned, at 0. When we talk about the short run behavior, we know that as the input approaches 0 from the left, so we're talking about this arm of the graph, and they're saying, taking on very small negative values, the function values will actually become very large in the negative direction. So you can see as our graph starts approaching 0 from the left-hand side, we're getting closer and closer to 0 here. As closer as we get to 0, you will see your y value starts plummeting downwards, right? So it's getting large, but in the negative direction, which means as you get closer to 0 from the left, that minus sign at the top indicates you're coming at 0 from the left. Your function values or your y values are heading towards negative infinity. If you look from the right-hand side on this function, as we are coming closer and closer to 0 from the right-hand side, you can see your graph is heading upwards, which means our function values or y values are getting really large on the positive side. So as x gets closer to 0 from the right-hand side, that's what that plus sign is telling us. Your y values or your function values are getting really, really large. So again, I had very briefly talked about this before, but what's happening, and we can go to Desmos to give you a closer look at the graph. You know, we can zoom in a little. So y equals 1 divided by x. Okay, so look what happens when we try to, you know, zoom out. Now, in that way, it almost looks like the line is going right on top of the y-axis, right? Like we are touching. But as soon as you start going closer, you will see there is actually a gap between the graph and the y-axis. So remember, this happens when you have a vertical asymptote. So at the y-axis where your x value is actually equal to 0, so right along this is a vertical asymptote. What is an asymptote? Well, basically it means our graph will get closer to this line, but it will never touch it and it will never cross it. So our graph will never cross this imaginary vertical line and go to the other side of it. It will never intersect it. And in this example for 1 over x, it happens to be at x equals 0 because remember, we cannot have the denominator be equal to 0. So your vertical asymptote is happening at that same point, x equals 0, or at that same value for x. So yeah, we have a vertical asymptote here. So that's kind of what they are talking about here. The behavior creates a vertical asymptote. It's basically a line that the graph approaches. The graph is approaching the vertical line x equals 0. As you know, our graph gets closer and closer to 0. Your long run behavior, of course, in this case, we are saying as x approaches infinity, your function value is approaching 0. So think about this. X is going to be approaching positive infinity on this side of the graph, but you can obviously see your y value is actually getting smaller and smaller. It's approaching 0. Same thing's happening on the left-hand side as your x values are going towards negative infinity. Your y value again is getting closer and closer to 0. So basically, as x goes to positive or negative infinity, your function value is getting closer to 0. And this is happening because we also have a horizontal intercept where your y value is 0. So there's another imaginary line right here where the graph gets closer and closer to it, but it will again never touch, never cross, and this will be at the line y equals 0, which is the horizontal asymptote. So you basically have a vertical asymptote at x equals 0, and you have a horizontal asymptote at y equals 0. And you know, that's common for rational functions to have both horizontal and vertical asymptotes. And later on, we'll also talk about oblique asymptotes, but you know, we'll worry about that as you get to that part. So again, remember, our x values are getting closer to positive and negative infinity, but the y value is getting closer to 0. And again, remember, these are imaginary lines. We don't actually see them, right? But we know they exist because of the behavior that the graph does, where it starts getting closer to these lines, but it's not crossing them, it's not touching them. Here are your formal definitions for vertical and horizontal asymptote. So a vertical asymptote of a graph is a vertical line. And since it is a vertical line, it will have the format x equals a, where a could be an integer value. And this is where the graph tends towards positive or negative infinity. So they're saying as your graph will get closer to this number a, your y value will start going towards positive or negative infinity. And you can kind of see that in this notation here. The horizontal asymptote kind of works in the reverse way. So we're saying the horizontal asymptote of a graph is a horizontal line, y equals b. Again, all horizontal lines have the format y equals, some number integer for b. And in this case, we are saying as the graph approaches the line, the input value gets really large, which means that your x is actually getting closer to positive or negative infinity, but your y value is approaching that value of b. So kind of like we saw 0 with the 1 over x example. This one over here, they're saying, okay, show us, with the notation symbol, how the long run and the short run behavior is working for the 1 over x squared function. The reciprocal x squared function, remember, is the 1 over x. So in this case, you will see for the long run behavior, as your x values are getting closer to positive or negative infinity, you will see it's approaching the x-axis. So that's the line x equals 0. That's where we have the horizontal asymptote. So you will see your y values are approaching 0 for the long run behavior. For the short run behavior, you can see as your x is getting closer and closer to 0. So, that's this part of the graph. So you can see our x values are trying to get closer and closer to the y-axis. That's where your x is equal to 0. Of course, you will see both of the arms of our graph are headed upward towards positive infinity. So your y values are actually going to become really, really large. And you can honestly just do a basic, simple experiment here. So think about if we're doing the function 1 over x squared, we can start with 10 to the second power. And you can see you got 0.01, right? We'll repeat basically the same thing with 1 to the 100th power, and again doing the x square. Okay. Well, it's doing scientific notation, but you should be able to see that means we are going 1, 2, 3, 4. And look again how small that number ended up becoming, right? So the larger your x value will get, the smaller your y value will get, which is what's happening right here when you get closer to the as x gets closer to infinity, the y gets closer to 0. And then to reverse that, you would then have to kind of do the calculation where you're saying, okay, if I have 1 over x squared and the y value is, 10, what will x be? If I have 1 over x squared and the y value is 100, what would my x be? Same thing, keep increasing that y value and see what happens. So in this case, if we just had to solve this as an equation, you would be doing square root of 1 over 10,000. And you can see what that answer came out to be, square root of 1 over 100. And you can see as the y value gets, well, I should have done it the other way around. Let me get this last one and then I'll talk about it. So you can see as the y value, which is the 10,000, as the y value gets larger, you can see our x started getting more closer and closer to 0. So that's that behavior which is happening right over here. So yeah, it's literally, you can just plug these numbers into your calculator and you can kind of see how some of that behavior pans out. Now, this next example over here is asking us, and yeah, they do kind of mention that there were no horizontal or vertical intercepts because our graph will not be crossing the vertical or the horizontal asymptote. All right, guys, so this example here is talking about sketch a graph of a reciprocal function shifted 2 units to the left and 3 units up, or up 3 units. Identify the horizontal and vertical asymptotes of the graph if there are any. Okay, so we know it's a reciprocal function. So obviously reciprocal function is of the form, y equals 1 over x. And then they are saying the graph has shifted 2 units to the left. So we know the shift happens on the horizontal axis, which means the shift would then affect your x value. So you would have the x plus 2 on the denominator. And then they also told us that the graph moved up by 3 units. So the entire graph moves up, right? Which is the effect that happens on the y value. So your plus 3 goes at the end. And of course, you can see they had that right over here. But then they're also saying you could find a common denominator. So, if this guy is over the denominator of 1, multiply this by x plus 2, to have that common denominator. And we would end up with 3x. 3 times 2 is 6. This would, of course, now be the common denominator of x plus 2. You've got your 3x. 1 plus 6 gives you 7. And that's basically how they came up with that other function. But that first one also works if you didn't want to give it a common denominator. But they're basically saying, okay, looking at the function that, equation we came up with, we're saying shifting the toolkit function would give us this graph. Notice that this equation will be undefined at x minus 2 because our denominator would become 0 if x was negative 2. So obviously, we know that's exactly where your vertical asymptote will be. And that's actually how you find the vertical asymptote. You take the denominator of your rational function, set it equal to 0, and that tells you where your vertical asymptote will be. And that's exactly what happens. You set this guy equal to 0, move the 2 to the other side, and you get x equals negative 2, which is your vertical asymptote. So again, we know then by our behavior that when the x value will get closer to negative 2 from the right and left-hand side, your graph will end up going to positive and negative infinity. In this case, they are saying when you're coming at negative 2 from the left-hand side, your y value heads to negative infinity. When you're coming at negative 2 from the right-hand side, your y value or function value is headed to positive infinity. So basically, let's do a rough sketch here. We know at negative 2 is where the vertical asymptoted, and usually we use, dotted lines or dashed lines to show imaginary lines. So that's your negative 2. So we're basically saying when our x comes in from the left-hand side to approach negative 2, your y values are going down to negative infinity. As you approach negative 2 from the positive side, your y values are going up to positive infinity. So, just using that idea of the reciprocal function. Now, remember, that's a very rough sketch. That's not an actual sketch of the graph. Then they are saying as the input values grow, which is your x values, the graph appears to be leveling off at the output of 3, indicating that our horizontal asymptote is going to be at y equals 3, which means, I'll just use a different color here. At positive 3, so 1, 2, 3, maybe somewhere here. We would say this is where the horizontal asymptote is happening. So of course, with the horizontal asymptote, then we know as the y value gets closer to the horizontal asymptote, your x will be going to positive and negative infinity. So does that mean these arms will now be more like this, where they get blocked by the asymptotes? So, kind of something like this. Let's take a look. Yep, that's exactly what's happening. So you can see right here at y equals 3 is our horizontal asymptote. And then at x equals -2 was your vertical asymptote. And you know, anytime you are graphing by hand, I always fall back to the X and Y tables because they will give you the best idea of what the shape of your graph will look like. But these kind of short run, long run behaviors definitely help us come up with some of those initial basics that we need. Okay, so same kind of thing happening here. They're saying sketch the graph and find the horizontal and vertical asymptotes of, again, we have a reciprocal squared function this time. So they're saying reciprocal squared function, of course, will be 1 over x squared. That has been shifted 3 units to the right and 4 units down. So what do you think this equation might end up looking like? 3, so you have your squared function, we already got that, has been shifted 3 units to the right and 4 units down. So what will we need to do to make that transformation happen? How do you move this graph 3 units to the right? With what? On the whole function or
On the X.
On the X? Very good, because the shift horizontally always happens on the X. Very good. What about the 4 units down? On the whole thing. Very good. All right, let's see if our graph will match what we see here on the textbook. All righty, let's get rid of this guy. We have y equals 1 divided by x squared minus 3. Okay, very good. And then plus 4. Shifted 3 units to the right. Okay. This was my x squared. I did my minus 3. No, it's not shifting it to the right. So I actually need to change that. And it needs to be x minus 3. So you see how the shift happened to the right? When I was doing it the other way, y equals 1 over x squared. That's the green, right? The basic squared reciprocal function. And then when I did minus 3, I was still at the center of my graph. I hadn't moved 3 units to the right, was because the minus 3, putting it after the x squared, is actually not shifting my graph because it's shifting the entire function value, not just the x. So for it to take effect on the x, like we did above here, you need to put it x minus 3 inside the parentheses. And then, of course, we had the, was it up or down? 4 units down, it should be minus 4, right? So 4 units down will be minus 4. So modifications here would need to be x minus 3 squared and then the minus 4. So look at the graph we have here in our textbook, and then look at the graph, and I guess I can get rid of this guy. Look at the graph we have here in Desmos. Now they do look similar, right? So it can sometimes be just making sure we type in what we think is the right answer, see if we're getting, you know, that shift and the downward movement that we wanted. And if not, then modify your function. But yeah, now you can see that since you have x minus 3 in the denominator, this is where our vertical asymptote will be at x equals 3. So right here is that vertical asymptote. So obviously, as the graph gets closer to x equals 3, the y values or the function values are headed up to positive infinity. For the horizontal asymptote, that's coming from this -4. So y equals -4 is where the horizontal asymptote will be. And of course, you can see as the y values get closer to -4, your x values are the ones heading to positive and negative infinity. So yeah, just how those asymptotes will work out. So here's your vertical Here's your horizontal asymptote. All right, guys, we'll continue with this. So obviously do not worry about the rational functions homework. Just try to get your 2.3 and 2.4 homeworks worked on. And then if you guys have any questions, obviously, please reach out and let me know. And otherwise, have a wonderful weekend,